Okay, this is going to be a much simpler little model, and I'm just imagining its pieces. Great. Okay, excellent. Excellent, excellent, excellent. Let's add them all. File new model. And this is going to be called continuous aging and agent IDs. Okay, here we're going to have unique IDs associated with each person. Okay, I'd like you to add a person class to the model. Okay, we're going to add this person class, and without prejudice, we're going to make people into circles this time, because this will be useful. Okay, circle. Here we go. Boom. Boom. Oh, you know what? I'm wondering, should we take a break? Okay. I hereby declare. Okay. So, folks, we in our last discussion we had noted that these designations we use for people in the population are ephemeral, the built-in designations. So who is population member 0 changes over time. Sort of like who is the first person in line for, you know, opening of a theater. It's also ephemeral. It'll change as tickets are handed out or what have you. Who is the person with ticket number 37 at a restaurant, fast food restaurant, will change. So what we're going to be looking at right now is capturing two effects. One is giving out persistent IDs to population members that will not change as long as they're remembered. They won't change as long as they're in the population or as long as they're remembered by someone else. The second thing we're going to be talking about, ladies and gentlemen, is continuous aging. So I'd like you, so we've created this model, we've added a person, and thus far we've just added a representation visually to them. But I'd like to add a parameter to them, which is going to be called birth time. Okay. So this is going to denote the time of their birth, and I'd like specifically to set the time unit of the model to be years. Okay, so that when we refer to their birth time, it'll be the time in years since the beginning of the model, for example. Okay. The second thing I'm going to do will be we want to actually add a function in here that's going to describe their age, okay? Their current age. So how did I do that? I went into general, I dragged a function, and this function will be called current age, okay? Drag the function, it's called current age, and this will be used to get their current age. The current age will be continuous age. It'll be changing over time. So this is going to return a value. That's what his job in life is going to be, is to compute a value. And the value it will compute is the current time minus the birth time. Okay? The current point in time minus when they were born. Because time is measured in years, this will be measured in what? Years. Take something measured in years minus another thing measured in years, would be that. Okay, great. And now we're going to go up and we're going to set the size of that circle to be reflective of their current age. So who can tell me, where do I change this? So here's the circle. I want the circle to grow as they age. Where would I click, and what would I do if I wanted to make their representation, the size of that circle, depend on their age? Okay, it's in the radius here. Good. Under position and size. And what would I do? Would I just start typing it here? Now you have to click this thing. And so I want to call this dot current age. Okay? This is a function. So it's calling my current age function. It doesn't need anything to do its job, but we still have to specify begin paren, end paren, just as if it was sine and we had to give it a number of degrees to take the sine of. Okay? Oh, thank you. Thank you. Yeah, let's think about this. Maybe we need to make it. Well, no, I think that may be about right. Let's do that for now. Maybe we'll have to put a scaling factor in. Okay, now let's go to main. Let's create a population of people. How do I do it? Drag. Good. What else do we have to do? Population of agents, size 100, be fine. And then for the initial time, we're going to specify between uniform distribution between people who are 65 years old and 0. So they were born, if they're 65 years old now and it's time 0, suppose we're, by default, any logic model start at time 0. We can go change that. We could get them to start at 2014. But suppose we start at a thing called time 0. When would, if they were 65 years old now, when would they have been born? Minus 65. And suppose the youngest of them is now just born, age 0. Okay? Minus 65 to 0. Okay? Now, if I wanted to be really specific about it and robust, I'd make it minus 65 times year. Make it really clear we're talking about years. But I'm gonna leave that out for here. Okay. Okay, ladies and gentlemen, shall we run this model? Let's lay these people out. How do we lay them out in a random configuration? Let's do the old tried and true method. Where do we go? Sorry? Where do I go? To lay them out in random configuration for the old method? Main and scroll down. Layout type, random. Okay? Should we run it? Let's run it. Boom. There we go. Well, can you see what's happening? You see circles of different sizes. Why do we see circles of different sizes? Different ages. But what do we also see happening? They're getting older. Question? TA support? It looks like TA is engaged. But oh wow, that's exciting. That's exciting. Okay, this is great. So let's go. You get a 3 for here.
I just went away.
Oh, it just went away. Oh, that's happy. Okay, try it now.
And it builds fine.
Okay, can I see this?
Of course.
Okay, random apply on startup. Yeah, this is good. Okay, so we have a population of people, size 100, population of agents, don't see anything wrong. And then this guy, person, let's get a person. Let's go look at that. Birth time and then current age, this time current age, And then this, and returns value, double. And that's birth time minus birth time. I don't see any problems. Okay, let's try rebuilding it. Okay, let's try running it.
Oh, that's better than before.
Oh.
Could be.
It built fine when I.
It built fine earlier.
Fine earlier. It just then when I ran it, it got the runtime error, and then like 3 times I did it, and then you got it.
Okay, well, maybe it knows its master. Okay. So building. It's a building. It's a building problem. It's a building problem. It actually said building error. So it's actually not a problem with running it. It's a problem with building it. So I just went and built it here, and now let's try it. I'd love to see it, but it won't do it for me.
My build was successful, and then I got
the
runtime exception.
Okay, but it definitely was not a problem with the model. It's a problem with trying to understand the model enough to turn it into something runnable. And so I'd say press build again, but that's weird. I'd love to see it again, but each time, yeah. Yeah. Oh. Oh. Oh, so you mean, in other words, you were... Ah, okay. Yeah, so in other words, I think you were in here and you click this. Yeah, you got to be careful with this one, because this one, sometimes it's not going to run the scenario you want. You would, like this, I bet it, well, it could be that it didn't have any run in there recorded, and so I bet that's it. If you haven't run it at all yet, if this is the first time you've run this model, it probably doesn't know what you want to run. Because this is for running, particularly for running things as you've run them recently or something like that. Yeah, I would do this. I rarely use this because it's confusing which one it's going to run, and yeah. Okay. So in any case, that was it seems a problem with sort of knowing what to run and build rather than that. Okay. So this is continuous age, folks. People are growing over age, and just to be clear about this, well, we'll take advantage of this more in some other models we may see, but suppose we were to want to add a state chart to someone that where we wanted to have their mortality risk vary with age in a continuous fashion. We could have a state chart mortality, right? Or state chart. It's not really mortality. It's state chart sort of life course, and this is alive, and then at some point there's a death transition, and here they have this continuous age, and we could define, if we wanted to do so, a so-called table function. This is a very useful thing. We're going to set this to be this death transition to be a death, to be a rate, and we're going to set the rate, the so-called hazard, the chance of dying, to be according to a table function based on their current age. So this would be mortality hazard, as we call it, the chance per year that someone will die. And we could define this in any number of different ways. In this case, maybe for the youngest years in life, we have a 1 out of 1,000 chance per year of death, but then that actually lowers by age 1 because it's really the earliest years, and then maybe by age 10 it's also very, very small, and then by age 20 it rises. Think of those rambunctious years. 35 it's gone down again, and maybe it remains down until till 50 when it starts nudging up again, and then it works up its way till 70 maybe, and I'm picking values here, picking somewhat arbitrary values, but the idea is that we can have this mortality hazard, and it actually will graph it out for us here. And this mortality hazard, we have all sorts of ways we could tell it. How do you interpolate it? Do you interpret it as sort of stepped values, or do you linearly interpolate it, or do you use a spline-based method, which is a method which has some nice theory behind it, and sort of does a smoother interpolation according to polynomial fit. And then you say, how do I handle out of range things? Do I just use the nearest value? Do I extrapolate? Do I use some sort of custom strategy, treat as an error? So in this case, what we're going to do is we're going to have this mortality rate be set by a mortality hazard. And this is a table function So it's a function, so we can look up our current age. So current age, and look it up within this to, oh, you know what? Did I do a rookie mistake? What an amazing thing. I feel sorry. You know where I put these things? I put them in main. They belong in person. Sorry, folks. I just cut and I just paste them. What the heck? I was wondering what is going on here. Okay, so there we go. The mortality hazard, well, that's a good question. Does that belong? It's not a parameter, so it causes less trouble than a parameter. Putting it in main, with parameters, there's several reasons to put them in main as opposed to person. And I still vacillate as to where to put a given one. One of the arguments for putting a parameter in main is if it doesn't differ between people, but that's just one of many. Another argument for putting it in main is that then you can set it from experiments. Another reason for putting in main is you don't have to specify it every time you add someone to the population. And mortality hazard, it certainly it's something shared between people, so that might suggest putting it in main. On the other hand, you don't have to worry about specifying it when you're adding people to the population, and it's something which causes in general less sort of awkwardness if we keep it in person. So I would tend to keep it together with person. We also don't have to worry about specifying it from experiments. So in my view, it kind of belongs best with the person because it's about the person, or it's about people. You notice that you can set mortality hazard. Mortality hazard is by default something which, if it doesn't differ between people, it's by default. See how it says static there? And what that means is, and that's why it's kind of grayed a little bit compared to this one, I think. Oh, no, I guess maybe they're the same color. I can't tell. No, I guess it's just that this means it's shared between people. It doesn't differ between people, but it keeps it with person because it's kind of something about personhood. So I would tend to keep it there, but I don't feel really super strong about it. But here, we're setting the mortality hazard according to their current age. And again, the current age was set the current time minus the birth time, okay? So this mortality hazard is being applied so that we have different mortality at different ages. And to find the mortality that applies at the current time, we look up their current age and apply the mortality hazard to that. Now, there's one fly in the ointment, and this had to do with a point I made yesterday. This transition has a rate changing over time. Yesterday, we had a transition which had a rate changing over time. What was that transition? Does anyone remember? It had to do with interacting state charts. Do you remember that? We had a chance of diabetes that changed over time, but it changed only at those points where another state chart changed states. And so that state chart is automatically notified. This state chart would automatically notify, hey, something has changed, wake up and smell the coffee, recompute your rate. But here, we don't have anything telling it. And so if we were to impose, just to sort of illustrate this point, suppose we were to make, for age 0, suppose we were to make the hazard 0, okay? And if I were to go run this model, unless something is changed in AnyLogic 7, I would expect it basically to have no mortality. And you see that the people here are not dying. You see the population size 100 still. No one's dying here. Why? Because they first enter in this state. This is a subtle point. Those wishing to become really familiar with AnyLogic should bear note of this. When they come into this state, this rate is computed. What's it based on? It's based on their current age. What's their current age when they first come in here? Well, it'll look up and it'll apply that rate from then on. It'll be applying their current age at the initial time, and from then on their mortality hazard will be based on that rate. So let's go look at for different people here in the population. So here we have people of different ages, and oh, I should have shown name, so it'll show the time here. Let's do show name for this guy, and then let's save it and let's run it. So here's a person that's, the first person in the population here. Okay, this person is comparatively younger. I'm going to look for a really young person. Take this one. Their mortality will occur in 3,000 years, or 3,000 years, something like that. Oh, no. Okay, I may be off here. What's the unit? Sorry, was that a decimal? Okay, I misread that, sorry. So their mortality is basically set by their initial mortality when they come into that state chart. I see. So this is 400, yes. So it's going to occur in, okay, this is actually specifying it, yeah. This is in the number of years until death will occur. And they're growing older and older, but they're not being updated with the newer mortality hazards. So in other words, as they're aging, their chance of mortality is supposed to be rising, but it's not right now. Oh, great. I left AnyLogic here. So it's not rising. So to make it rise, the reason is when they enter that state, that's when the mortality is being determined for them. And nothing's telling them something has changed at that point, okay? That something has modified, recompute mortality. So to get it to do that, you need to tell it to essentially recompute your rate. Recompute your rate. And there's several ways to do that in AnyLogic, but the easiest way to do it in a way that helps us be more friendly is to actually have a transition that goes from that state to that state, leaving the state. So here we have our little thing here, and the issue is when they come into the state, their mortality hazard is determined on a one-time basis right now. It's determined based on their current age when they start the simulation. If everyone started with age 0, no one would die at all because the mortality hazard is 0 for that, as in my latest update. So here, when they come in, their mortality hazard is being determined and it's not being recomputed. If we wish it to be recomputed, we can do so by setting a transition that leaves this state and comes back in. And I'll go implement that. I'm going to go double click on this here, and then I'll drag it down here. Here we go. We're going to set this to be going off at a timeout. Every 1 year, it'll recompute the mortality hazard, for example. So this will be called Recompute Mortality Hazard. Okay, so it's not, even though continuous aging is going on, even though people have double precision age, and at any one time we may read the age off for someone in a continuous fashion, the mortality hazard is only being computed over time, being updated every year. So it's being updated once a year. Okay. Oh, we didn't remove someone from the population when they die, so let's go do that. So in this death state, this final state, how can I remove the person from the population? Give me the formula. We just did this. Main dot remove underbar population. Okay. It's in the action associated. Oh. I'm doing it with the transition. I meant to do it with this state here. It's the action associated with the state. With this state down here. Okay? Remove population. Okay. 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 So, we have to remove us. We have to point it to this. Yeah, sorry. Remove us from the population. I did this. This is in the final state. In the final state. Okay? So, sure, here. There's a timeout, and all it does is it's a timeout of 1, it leaves and comes back in. And the whole purpose of it is to get it to recompute this transition rate. Sure. And it does so every year. Exactly. So every time someone is aged by a year, it recomputes it. So now we have people dying, and those that are older will tend to die off. As people grow older, they're dying, and we have this mortality hazard being handled, but it's only updating once a year right now. Yeah. Yeah. No, it'll actually be, it's a good question, but the question was, do you have to get it to first recompute their age and then the mortality hazard? This is the formula, the rate formula for this exit transition, this transition for mortality. And what's going to happen by coming back into the state, the rates associated in conditions associated with any transitions leaving this state will be recomputed, okay? When you come back into the state, those rates are recomputed. This is the formula for the rate. So it will call current age, get their current age, and it will apply the mortality hazard table function to look up for that age what's their risk of death per year. And it will then use that.
The update of the mortality hazard is only happening in the other transition. So why would it there?
Okay, so
It's not named there, but
okay, when this transition here that's shown with kind of looping back to alive, that leaves the state and comes back in. And it's when you come into a state that it's recomputing the rates for all of the transitions that leave that state. And so the rates specified for any transition which leave alive will be recomputed at that time, including this one that says death, this one that's highlighted here. And its rate it'll be given by this formula, and that formula is reevaluated at that time, okay? So it's recomputing it.
if you wanted to, let's say I have several like comorbidities.
Yep.
And I need to make sure that every year updates the
Yep.
risk.
Yep.
Then instead of having that for each one, could you do like one event that could every year
Oh yeah.
update?
Oh yes. Yes, you can do that as well. And I believe, in fact, Maria, I'd have to double check this, but I believe that that even having one of these in a given person will lead to that all the rates elsewhere and all the other state charts to be recomputed as well. I'd have to double check that. Perhaps we'll add a little bit of clarity to this. I'm gonna do something. I'm gonna take this model, and I'm going to actually define it to have a population size given by a parameter, and I'm going to run it with a single person in it, okay? So it's going to be based on a population size parameter, and I'm going to add that parameter here. It will be called population size, and it will be an int, and its default value will be 100, and we're in fine shape, but we're going to add in a new experiment called single person that's just going to have a value of 1. So what did I do? Let's go through that again. I went to main. I added in a parameter called population size, and I made it an int because it's a count, and I made its default value be 100. Okay? And then I added a new experiment called single person, and I made it a population size of 1. Okay? Yes, I'm going to make population use population size, and I did, in fact, but I should have emphasized that. Population has initial number of agents be population size. Okay? Okay? Okay. So initial population, this population has an initial number of agents given by population size. I just want to run this model with a single agent because I think it'll be clearer. Okay. So here, if we run the model, we will see a single agent growing over time, right? Okay. And then it disappears. Great. Okay. But doing this will allow us to sort of have a closer observation of what's going on. So, Maria, one way to, and this is a very important trick. It's a trick I've used quite a bit in AnyLogic, and it's important that you be aware of it. So, if we wanted to find out, Maria, when this current age is being computed, when this expression is being recomputed, you notice it calls current age. So we could put into current age something that prints out, I've been called. You know, it inside current age function, it says trace ln, I have been, you know, current age has been called at time and give it the current time, okay? Okay, there we are. So current age has been called at this certain time. We could have it print that out. And that will tell us when it's being used. And the only place it's being used, oh, I'm sorry, it's being used for this guy as well, isn't it? It's being used for the size of the oval. Yeah, so it's being used in two places, here and over there. This actually wouldn't be that helpful, but it'll illustrate the point. So it's actually being called. Okay, it's being called over time at these times, okay? Those times exactly. Now, if I wanted to find out when this particular expression was being called, this particular expression, I could use a similar principle. I could actually have it call a function, and the function will return this thing, and it will further print out that information, right? So why don't I say, I'm going to create a function called Compute Mortality Hazard, and this is going to be a function. So in this transition, I could have something called Compute Mortality Hazard. This is going to be a function, Compute Mortality Hazard. It's going to return a value, which is a double. Okay? And I'm going to call it from here. Hazard. Yeah. And it's going to return a double. Yeah? And its job in life is just going to be to evaluate that expression that used to be here, but it's going to also print out when it was called. Trace ln, compute mortality hazard was called at time, and I'm going to print out the time. This will tell me exactly when this is being recomputed, exactly at what point. Okay, so this is a function. We just introduced a function. It returns a double, and we're calling it from here.
What are we returning? I'm so sorry.
We're returning the exact formula that used to be here.
Okay.
So I'll put up this thing here. This is what it prints out.
Got it.
Okay.
And we can get rid of it in the other place?
Right. We just call the function. It's returning that value, so all we have to do is call that function, okay? So, folks, to be clear here, this is a trick to observe when it's recomputing this. So it'll print out, it will tell us when is this being recomputed. It's going to compute the mortality, it's calling this function called Compute Mortality Hazard. This function is returning a value, that's all it does, and what does it doing, it's going to return that value, which is the original value that was here, but it's also going to print out something that says I was called at this certain time. Okay? Okay, who needs help with this? Yep, help here. So the goal is, if this was just being called by itself, if we just had some expression here, we don't know when it's being called. By calling a function, we can tell it, we can have it print out when it's called. Yeah.
So I think I did something wrong. The current age is undefined in type person. It worked before, but I did something just now that screwed it up. So basically what I did was I put here,
yeah,
and then
yeah,
and I deleted the rate there, but then over here is where I now
okay
do.
Okay, let me come around here. Okay, okay.
The current age is not being defined.
Current age is there.
Is there.
Oh, but I think it's spelled with a lowercase a here.
Ah, okay.
And with an uppercase
so
a.
this is me and a typo. All right, got
Yeah,
it.
it's just a typo.
Okay.
So make it current age.
Exactly.
Yeah, yeah.
All right, and let me do that in the other place too.
Okay.
Oh no, it should be gone elsewhere now, right?
Okay. Cannot. Okay. So it says cannot return from null to double. Okay. So what's going on here? Oh, you need to have as the rate. You need to do compute mortality hazard. Okay.
Not down here in the action.
Not down there.
Okay. And does it have a semicolon at the end?
No. Okay. It's just a value. Got it. Okay. Okay. Would you like help?
Yes.
Okay. Great. Okay. Right. Compute mortality hazard. Okay. Okay. So what you actually just want is compute mortality hazard like that. Okay. And then you're done with it. Okay. Okay. Sure. Okay, folks. Yes. Yeah. Sure. It's this. Okay. So, folks, this is to answer. I'm trying to answer the question that Maria raised about when this specific transition is being evaluated. How are we going to find out when this transition is evaluated? When is its rate recomputed? Well, the clearest way to do this, the way that will be definitive evidence as to when it's computed, is to have every time that rate is computed, it print out something that says that it's being recomputed at that time. So all this mechanism of getting it to call this function is just to do that. Okay? It's just to get it to print this out. Sure. The right-hand side is just this. Oh, well, yeah, it's supposed to. So if you run this thing with a single person, just a single person, what you should see is a complete specification of when this compute mortality hazard is being called. And let me get it to display that window again. So it is compute mortality hazard is being called at time 5. It's being called at time 4. It's being called at time 3. Let's okay. Okay. So current age here is also printing things out. We don't need it to print things out anymore. That was just an illustration. So if we comment this printout from current age out, it may be clearer. So current age doesn't need to print anything anymore. It's only compute mortality hazard. Okay? Slash in front of it. It's just like on the screen here. Okay? It's being called from this transition for the rate. Right. Okay, folks. So what's happening is Maria raised the question: when is this transition being updated? And I said this transition is being updated when this other transition is being taken, because you're coming back into the state. And when you come back into a state, all the transitions out are being recomputed. So my goal here was to show exactly when is this transition being recomputed? Exactly at what point is this transition being recomputed? What times? Because I wanted to see when is it updating its mortality hazard based on someone's age. After all, we have people's age changing continuously here. And the question is, when does it really notice that in terms of updating the mortality hazard? So what we did is to figure this out, to figure out when this rate was being recomputed. We have this expression for rate here. And so I said, rather than just computing the expression directly, looking up in mortality hazard, let's call a function. And this function will look it up and return the right value. But in the meantime, it will print something out saying, I've been called. And then every time it says, I've been called, we know it's been recomputed. We know it's recalculating the rate. And when I run this, what we'll find is that that rate is recalculated at exactly these times, these integer times. These are the times where what goes off, where this other transition is going off.
You're calling it twice in every year, right?
It's being called twice in each year, yes. Now, why it's being called exactly twice, I'm a little bit unclear. That's probably what's going on, yeah. Yeah.
When I turn that transition off, like it doesn't, I think what's happening.
Exactly. It leaves and it's recomputing it then, and you come back in. But the point is, if we didn't leave this state at all, if we eliminated this, when would it be recomputed? If we just had this, when would it be computed? First time they enter. And from then on, their mortality hazard will be the same. They're aging, but it's not recomputing their updated risks. Let's try it inside. I've tested in previous versions of AnyLogic, and it didn't work then. But things change, and let's try that. So single person. This is an inside transition. Oh, it is working. Nice. And it's only doing it. Okay. It's okay. That's interesting. Yeah, it's only doing it once. That's a great discovery. Wonderful. Okay. So. Sure. Suppose we wanted to update the mortality hazard suppose we wanted to update the hazard that is known to obtain for people every 3 months. How do we do that? Yeah, we'd set the timeout associated with this transition to be 3 times month, right? So every 3 months, it will recompute this mortality hazard. And I know this seems like a strange thing. I mean, we define this function, and we get the function to report. Whoa. Okay, now that's interesting. I did a timeout of 3. Oh, well, of course, right. It's not going to be, it's going to be much more frequent and not necessarily on year boundaries, right? Okay. Okay, so now it's computing approximately 4 times a year, right? 1, 2, 3, 4. 1, 2, 3, 4. So I want to apologize if this was confusing to people. I want to make a few very high-level points. This is all an exercise to capture the fact that we could capture continuous aging. We could capture the fact that people age over time in a continuous fashion. Okay, we don't have to just divide people up into age categories. We don't have to divide them up into only integer ages and update for everyone what their age is on a regular basis. Instead, people could just report their current age. They could just say, upon demand, I am 23.35926 years old. And whenever needed, I can ask for someone's age. That's useful when we want to slice and dice the population according to age in very fine categories. But there's an issue that comes up with that. And I tried to deal with it here. There's a risk, a hazard that comes up with it. And that is that if you are setting values for rates of transition that depend on your age, and this is being updated conceptually all the time, then it's not going to automatically recompute your rates. If we eliminated this altogether, what would happen? Only going to calculate it at the very first time in the model. And your initial age is going to dictate your mortality hazard then, and that's what's going to apply for the balance of your life, which is not what we want. So to get what we wanted to introduce this sort of transition. And initially I thought it had to go outside, and actually in AnyLogic 7 it seems it's perfectly happy going inside, and it has some salutary benefits. And I thank Maria for asking about that. But there was still the unsettling question, well, I think this is how it's going. What is it actually doing? What is this model actually doing in terms of when is it recomputing this rate? And my point is, you don't have to leave that up to chance. You don't have to leave it to guesswork. You don't have to leave it to going through the manuals. You don't have to leave it to watching videos online. Instead, you can go and you can get it to tell you when it's recomputing it. How do you get it to tell you when it's recomputing it? Instead of putting a hazard in here based on some expression, you call a function. Why do we call a function? What does function have to do with it? Because a function can return the right value, and that's great, but it can also print something out at the same time. You see the point? That if I can't tell it, watch this, if I put for the rate trace ln, I am computing the rate, and then I said 0.03, or I said, mortality hazard of current age, what do you think would happen? It would say, no, it can't do that. You can't print something out here. You can't, are you kidding? You can't do something here. It doesn't know what to make of that. I can put this, but then it doesn't print anything out. I don't know when it's recomputing it. Is it recomputing it? Is it recomputed frequently or not frequently? I don't know. So what I can do is I could call a function. What does calling that function do? Well, calling the function just returns the appropriate value. It's the same thing that was in there before, but in addition, it prints something out. And so this function, its job in life is to return this value for sure, but it can also have the very helpful benefit of printing it out. And that can tell me unambiguously exactly what is going on, exactly when this thing will be run, okay? It will be printing out here. It will tell me precisely when it's calculated. And that's in my favor. I want to know when is this being recomputed. At what point is it really calculating this rate? And to what degree is it just using the value it had originally? And I can find out, oh, right now it's computing every 3 months. If I remove this, it's computing it just a single time. Just a single time. That's not what I want. That would imply people have the same risk. They come into the world at the beginning state of the model, and they have the same risk from then on. That's not what we want. We want their risk of dying to change as they age. And this is the way we get it, by a self-transition like that, and we set the rate of that transition to reflect how frequently we want things to happen in the model. Does that make sense? Okay, yeah. Yeah, the birth time, yeah. Yeah. Okay, so the idea here with birth time, thank you for the question. So the question was, there's this birth time parameter. What does that have to do with time of birth? So some of you are from a health science background. And you know that if you work with data, you can, suppose we have data on, so we work with large-scale provincial databases on diabetes and end-stage renal disease. And we get data from our Ministry of Health across the population on when people got diabetes and when they were diagnosed with diabetes and when they were diagnosed with end-stage renal disease, right? And we can ask for data of that sort in basically two forms. We can ask for their birth year and then the year at which they got diabetes, right? And the year at which they were diagnosed with end-stage renal disease. And that allows us to compute their age at which they got them, right? So if they were born in 1971 and they were diagnosed with diabetes in 2001, they were of age 30 when they were diagnosed with diabetes, right? We can compute it that way. Or we could just ask them to provide us with the age at the time of diabetes diagnosis, and they'd give us 30, right? What I'm doing here is conceptually similar to that first strategy. We're getting someone's time of birth, and then that allows us at any given point to say how old they are. So it's just like if you had someone's date of birth, you could say how old are they in 1974, how old are they in 2001, how old are they when they were diagnosed with end-stage renal disease in 2011. They were 30 in year 2001, and they're 40 in year 2011. We can do that with data, and we can do it in the model. So this birth time parameter is used to allow us, whatever the current model time is, we can figure out how old this person is because we know when they were born, right? So it's just as if you had suppose you had a longitudinal study and you recorded the baseline characteristics of the population for each person, you recorded their birth year. Then at any given time during that study, you'd know what age they were, right? And it's exactly the same thing we're doing here. We're recording their birth time, and where is that set in the model? If we go to main, we go to population, we set their birth time, and that means that at a given point we can compute their age. Here we set their age by implication to be between 0 and 65 by setting their birth time between minus 65 and 0. Time starts at 0, and therefore some people are as old as 65 because they were born at time minus 65. Some people are as young as 0 because they're born at time 0. Now, in a model which has births occurring in it, what would their birth time be? It would be the time at which they were born. So, and actually, if you added them to the population, when you add them, remember we could specify when we added someone to the population, we could specify their sex, we could specify their ethnicity, or we could specify their mother. We just add this as a parameter to be specified, their birth time, and we would give the current time. So then, from then on, we would know how old they are, because we know the time they were born, and maybe that time was, time 200, and now it's time 230, so we know that they're 30 years old. Does that make sense? Yeah. So in general, we're going to do that. In this case, it's not quite as interesting because we're not adding people into the population. But if we were to do that, we'd record their birth time at that point, and from then on, we know how old they are. Helpful? Okay. Just to do that, I'll just add, birth arrivals. Okay, here people are coming in to the population. They're coming in, and they're coming in at a certain rate. And what's that rate? It's 10 births per year. and we're going to add to the population this dot add under bar population. We'll add in someone according to the current time. So whenever a birth goes off, whenever there's a birth represented, we're going to add a person to the population with this being their birth time. Does that make sense? And then they get added, and they're all getting added up there because I set them. I didn't set them to be laid out randomly. But look at all these people coming in. There's 646 people. And this person has died, but if we go up, we could stop the population. Let's go down. And person 700, this was someone born during the model. They were born at time 189. It's time 190 here. They're just under 2 years old. Is that helpful? Okay. So that's a way of kind of slicing the population up by age in as fine a way as we want. So we could summarize things about people who are within the first 6 months of life, some people within first 2 years of life, some about people in 5-year age categories. Slice and dice as you see fit. We have that information as fine-grained as you want it. The only trick is you got to be a little bit careful when doing things like this, computing things which change over age, because age is changing all the time. Okay? Apologies for the confusion, but I want to use this model to finish off, and we can do this in less than 5 minutes. Maria's question, where is the ID? People's names seem to be ephemeral. People come into the population, disappear from the population. Who is population member 200 will be changing all the time. How do we give people a sort of persistent name, a persistent identifier? Let's do that. This will be the final thing for the morning, and then we'll break for a much-needed lunch. Okay, so go to person, and we're going to do something you haven't probably seen before. And this, too, will stretch you. We've added functions now. Functions return values, they print things out, and hopefully that's probably new to most of you. Let's add a new variable in, and this is going to be called ID. It's interesting, it's not a parameter, and it's a variable. Maybe, I'm just thinking there's 2 different ways I could do it. I'm going to, I actually think it would be cleaner. I'm going to delete that variable, and I'm going to do it as a parameter, okay? And I'm going to actually make this a separate